Hi everyone, so today we're going to look at applications of logarithmic functions, and really we're going to be looking at applications that use log scales. So when would we use a log scale? If we were going to compare something, for instance a high school population, then the way that you would talk about two high schools would be you'd say one school has a couple hundred more people than the other. Or you might say that one school is twice as big as the other. But really you're dealing with two numbers that are going to be reasonably close to each other. High school is generally probably under 2,000 people, especially around here, and they're going to be roughly the same number. When you're dealing with something with like earthquakes, it's not appropriate to use that same unit of measure because an earthquake with intensity 10 is very difficult to compare to an earthquake with intensity of 1 billion. Okay, there's a huge range there. And that's why we would use a logarithmic scale. So logarithmic scales are going to be useful for plotting and comparing quantities that span a very large range, okay, several orders of magnitude. And we'll get to what several orders of magnitude means in 1 minute. So if data were plotted on a logarithmic scale, a value of 1 would actually indicate 10 to the 1. So that 1 actually means 10. A value of 2 indicates 10 to the 2, which is 100. If you plotted a value of 3, that would actually indicate 10 to the 3, so 1,000. Okay, a value of 12 would be 10 to the 12. Okay, so as you move up one single number on a logarithmic scale, you're actually increasing it by a factor of 10. So that value that you're stating actually refers to the order of magnitude. And when we're dealing with these orders of magnitude, that's when log scales become useful. So we're going to look at 3 different examples of log scales. And the first one is measuring an earthquake's intensity. So if you've ever heard them talk about an earthquake on the news, chances are you've heard them talk about a Richter number. So the Richter magnitude scale, or more correctly the local magnitude scale, assigns a single number to quantify the amount of seismic energy released by an earthquake. It's a base 10 logarithmic scale, and it's obtained by calculating the logarithm of the combined horizontal amplitude of the largest displacement from zero on a seismometer output. You don't need to understand anything about earthquakes. Okay, we're really just going to be looking at the math behind them, but that is what a Richter number is. Okay, down here I have a little chart just to show you the different Richter magnitudes and what effect they would have. Okay, so something that's around 2 is a minor earthquake, generally not felt. There's quite a few of them per day in the world. If you move up, when you get to about 4, that's when you've got things shaking inside houses. Significant damage is unlikely. Okay, and we get quite a few of those per year. And then when you get up to things like a 7, somewhere in there, it can cause serious damage over large areas. And we don't have very many of those in the world per year. And as you go up, you can see that it gets worse and worse. If you're getting to a 9, it's devastating in areas several thousands of miles across. And there's about one of those every 20 years. So we get a lot of the little micro earthquakes. Once you're getting up into bigger earthquakes, they're rare or they never happen. But even just moving up a Richter number of 1 is a fairly significant difference between the amount of seismic activity. So the Richter scale measure of an earthquake is given by the formula m equals the log of I over I naught, where I is the intensity of the earthquake being measured, I naught is the intensity of a low-level reference earthquake, usually 10 to the negative 4, and m is the Richter number used to measure the intensity of earthquakes. So if we want to compare 2 earthquakes, then we would create one of these formulas for each earthquake. So here I have a formula to represent the magnitude of earthquake 1 And here I have the formula to represent the magnitude of earthquake 2. If we're comparing the two earthquakes, then what we would do is we'd subtract those Richter numbers to see how different they are. So doing M2 minus M1. And what I did to the left side equation, I'm also going to do the right side equation. And those are I's. And now I have on this right side 2 logs being subtracted, and those logs have the same base. So I can actually use the quotient law of logarithms, which tells me that I can take the log of the argument of the first divided by the argument of the second. So I2 over I naught divided by I1 over I naught. And since they both have I naughts on the bottom, they would cancel out, and I'd be left with M2 minus M1 equals the log of I2 over I1. So this is actually the formula that we can use to compare two earthquakes. Inside here is the ratio of intensities. That is the Richter number of the second earthquake, and that is the Richter number of the first earthquake. So here's example 1. We have the famous Loma Prieta earthquake near San Francisco that struck in the middle of the 1989 World Series between the San Francisco Giants and the Oakland Athletics. Okay, it measured 6.9 on the Richter scale. How much more intense was this earthquake than the standard earthquake? Round your answer to the nearest tenth. So we're dealing with one earthquake and we're comparing it to the standard earthquake, so we're going to use that first equation, that m equals the log of I over I naught. It's asking you how much more intense. So that's really asking you for the ratio of intensities. Which is really the I over I naught. Okay, so that's what you want to find. And they give you the Richter number, so they give you m. Okay, so we're going to sub in our m of 6.9, and we're trying to isolate that I over I naught. And we're not going to isolate an individual I or anything, we're going to isolate that entire ratio. So to get it alone, remember when we have log equals a number, we can just switch to exponential form. So 10 to the power of 6.9 equals I over I naught. And then we can actually solve this by just typing 10 to the 6.9 into our calculator. And therefore, the 1989 earthquake was 794,382.3 times more intense than the standard quake. So for part B, it tells us that this was not the most intense earthquake to strike the San Francisco area. There was an earthquake roughly 22 times as intense that struck in 1906. What was the Richter scale measure of this quake? So we're comparing two different earthquakes here. So we're going to use the second formula that has two different Richter numbers in it that we use for comparing earthquakes. And we're comparing our new earthquake to our old earthquake. So the old earthquake is going to be M1. So that's going to be that 6.9 from part A, because that's what we're comparing our new earthquake to. In the question, they told us that this new earthquake was 22 times as intense. So they actually gave us the ratio of intensities. So they gave us that I2 over I1. So we're going to sub that in for 22. And then we just have to isolate our second Richter number. So we have to isolate that M2. So I'll fill everything in first. And then I moved that 6.9 over to the other side. And I'll just round this to 1 decimal place. And I get a Richter number of 8.2. So therefore, the earthquake in 1906 was 8.2 on the Richter scale. The next application we have is logarithms and sound. So it's very similar actually to the formula that you use for the Richter scale for comparing two earthquakes. Here you're comparing two different sound levels. And you'll notice that there is this 10 in front of the log of the intensities. But that's really the main difference is we use beta to represent sound levels. It's measured in decibels. And then there is that 10. So once again, here is a chart to show the different decibel levels. Conversation from a foot away, so normal conversation, that is 60 decibels. And once you get up to a rock concert, a jet engine, that's when you're at the human pain threshold. Stereo, 80 decibels. Power tools, 110 decibels. Okay, so it is interesting to see that. A library nice and quiet down there. So doing questions for this one is very similar to the earthquake one. So here we have a Mumford & Sons concert that Miss Anjos attends at the Molson Amphitheater. The peak sound put of the amplifier is 145 decibels. How much more intense is this than the sound of a normal conversation? So once again, they're asking how much more intense. So they're asking us to find that I2 over I1. And we're comparing it to normal conversation. And if you look back at that chart, normal conversation is 60 decibels. So really, at this point, we are subbing everything into our formula. And we're finding that ratio of intensities right there. So we sub in the 145, we sub in the 60 that we're comparing it to, and now we just have to isolate I2 over I1. So we've plugged in our numbers. I subtracted the 145 by 60 to get 85, and then we're trying to get this ratio alone, so I divided both sides by 10, which got me 8.5 equals the log of the intensities. And then to isolate the intensity, I switched to exponential form, and then I typed it into my calculator. And that got us that the concert sound level was 316,227,766 times more intense than the sound level of normal conversation. So, a huge difference there between normal conversation and this concert. So if you guys go to the next video, you'll see the last application, which is the pH scale.